So welcome again. As promised in the previous class, we are going to give two examples on determination of the scalar potential function when you are given a vector field in 3 dimensions. So examples. So example 1, find a potential for the vector field given by f equals to y squared y squared I plus 2xy plus e raised power 3z j plus 3y e raised power 3 zk. So this is a problem. So we give a solution from the definition of a scalar potential on given vector field. So solution, I will say, we know that a potential function f exists for f for this vector field if and only if this equation is satisfied. So this is the main definition. So what we are going to do, we are going to write the gradient of this potential function and then equate to the vector given by f. So y squared I plus 2xy plus e raised power 3z I j plus 3y e raised power 3z k should give us the gradient of this one. So we'll have partial f partial xi plus partial f partial yj plus partial f partial zk. So that's what we have in this equation. So the next thing, we simply equate the components of I, j, and k on to ensure that this equality makes sense. So this implies that partial f partial x equals to y squared, partial f partial y equals to 2xy plus e raised power 3z, and then partial f partial z give us 3y e raised power 3z. And then you call this question 1, call this one question 2, and then call this one question 3. So that's what we have. Now our main interest is to find f. That's our objective. This value of f. So to get f from equation 1, we integrate both sides with respect to x. So integrating equation 1 with respect to x, we get so integral of partial f partial x with respect to x equals to the integral y squared dx. Now this will give us f, and then this will be x y squared, and then plus. Now constant of integration, but now because we're dealing with a function of 3 variables, because we are doing integration with respect to x, now this constant will be a function of y and z. Call this one question 4. Okay, so we are going now to integrate, to differentiate equation 4. Now differentiate equation 4 with respect to y, i.e. we'll have integral partial f partial y equals to this one now will give us 2xy, and then plus this will be partial g partial y, or you can write this one as 2xy plus g sub y of y z. This just means the partial derivative with respect to y. So call this one equation 5. Now you see equation 5 defines partial f partial y. Also equation 2 defines partial f partial y. So equation 5 equals to equation 2, because all of them are defining partial f partial y. So therefore, the expression for partial f partial y in 2 and 5 can be equated, and we say here is 2xy e raised power 3z we equate it to 5, we have 2xy, and then plus partial g partial y. Now you see by this equation, if we equate this and this cancels out, so that we have partial g partial y equals to e raised power 3z. And if we call this one equation 6, so to get g from equation 6, simply now integrate both sides with respect to y. Now integrating equation 6 with respect to y, we get integral of partial g partial y dy equals to integral e raised power 3z dy. So left hand side will get g, which will give us this one will just be y e raised power 3z, and then plus say k or C, which is a constant of integration. So call this one equation 7. And you see equation 7 gives us our G, and really that is what we really needed to have our function f. So using 4 in 7, using 7 in 4, using equation 7 in 4, then our f of x, y, z will be given by, so 4 we had x, y squared and then plus g of y, z, which is y e raised power 3z plus k. So therefore, that is our potential function. And then last example on this same problems involving evaluation of or finding of potential function. Number 2, find the potential function for the vector field f equals to e raised power x cos of y plus yz I plus xz minus e raised power sin x sin y j, and then plus xy plus zk. So this is the next problem. So here we say from definition, solution, we know that a potential function f exists if and only if this vector field f is gradient of this potential. So this is the definition. So what we do now, we write our vector field, then we equate it to the gradient of this potential function. So we'll have e raised power x cos of y plus yz I plus xz minus e raised power x sine of y j plus xy plus z k. So the gradient of the potential, which is the same as partial f partial xi plus partial f partial yj plus partial f partial zk. So that's what we have. Let's just have by this definition here. So we create components of I, j, and k so that this vector equality makes sense. So this implies that partial f partial x is equals to e raised power x cosine of y plus yz, call it equation 1, and then partial f partial y equals to x z minus e raised power x sine of y, call it equation 2. And lastly, partial f partial z equals to x y plus z, call this one equation 3. So that is step 1. For the vector equality to make sense, then the components on either side must be equal. So now we start by integrating the first equation with respect to x so that we get f. So we say integrating equation 1 with respect to x, we find, so integral partial f partial x dx equals to the integral e raised power x cosine of y plus yz is with respect to x. So this will give us f equals to e raised power x cosine of y. There is no x, so it will just have x, y, z, and then plus. Now, because this is a function of 3 variables and we're carrying out integration with respect to x, then the constant of integration becomes a function of y and z. Call this one equation 4. Now, so we then again differentiate this equation 4. So differentiating equation 4, we have differentiate equation 4 partially with respect to y. So this will give us partial f partial y. This will be now minus e raised power x sine y plus xz, and then plus, so this will be partial g partial y, or you can write g sub y of y z. So call this one equation 5. Now equation 5 and equation 2 are the same. So equation 2 equals to equation 5. All of them are defining partial f partial y. So that tells us that we can equate equation 2 and equation 5. So equation 2 is xz minus e raised power x sine y. We equate to equation 5, which is minus e raised power x sine y, and then plus xz plus partial g partial y. So this tells us that this and this cancels out, this and this cancels out, so which implies that partial g partial y is equals to 0, i.e. g of yz is just a function of z. We are saying this when we get that, remember the differentiation of a constant is 0. And when we are dealing with partial derivatives, so partial g partial y giving a 0 means that now it's a function that doesn't involve y. And because this was g of y z, then must be that means that g must just be depending on z alone. That's why we are saying this one. So therefore, let's again differentiate equation 4 now with respect to z, because this one has not helped us to find z g properly. So with respect to z, this would be 0. So this will give us xy. So partial f partial z will be equals to. So this will give us 0 because there's no z here. So this will be xy and then plus partial g partial z. Because now this was a function of two variables, y and z. So call this one equation with 7 from our numbering. 6, call it 6. So, and then equation 6 and equation 3 are the same. Hope you can see all of them are defining partial f partial z. So equation 3 equals to equation 6 because all of them are defining partial f partial z. So this means we can equate 3 and 6 and say 3 is xy plus z should give us xy plus partial g partial z. And when you equate this, you see that xy cancels out, so that we get partial g partial z will be z. Call this one equation 7. And then partial g partial z equals to z. Now to get j alone, we now integrate with respect to z. So integrating equation 7 with respect to z, we get, so I'll have the integral partial g partial z equals to the integral of z dz. So we are integrating with respect to z. So left hand side gives us g, and then this will be z squared over 2. Now this plus a constant of integration k. So therefore now our function, so if we call this one 8, we can now successfully give our function, because that's what the g was the only problem in equation 4. So therefore our function using 8 in 4, we have the potential to be f of x, y, z equals 2. So 4 we have e raised to power x plus y plus x, y, z and then plus g, which is z squared over 2, and then plus a constant k. So this is the potential function for that given vector field. So that's how we solve that given problem. So thank you, and let's meet in the next class.